All right, here we are, kids. Another episode of Stats with Glenn. Believe it or not, we are up to Chapter 9. How wild is that, kids? Chapter 9 is a special chapter. I don't think I say that about every chapter, but even if I do, this one really is a special chapter. Chapter 9 is on something we call statistical power. Statistical power is different in a lot of ways than the other hypothesis testing concepts that we have gone over. Statistical power. Okay, so statistical power is a process, or it's a concept that is not actually carrying out a hypothesis test. So in the last two chapters, chapters 7 and 8, we were actually carrying out hypothesis tests. For chapter 9, we're going to address the question of statistical power. Power can be thought of as the probability, and so P parentheses means probability of rejecting the null hypothesis if you were going to carry out the hypothesis test. Okay, so this is a different kind of question. Instead of carrying out the hypothesis test and trying to figure out if some prediction is supported or not, in computing statistical power, we're trying to get a sense of the probability of rejecting the null hypothesis or finding statistical significance if you were going to carry out the hypothesis test. This is kind of like a real statistician's kind of issue. And if you end up finding yourself as a researcher or as a statistician in your profession, this is the kind of question that becomes very important. Let's say you're going to design a study. And let's say right now in the age of coronavirus, you were going to design a study to try to come up with a vaccine. And you want to test whether a vaccine is useful compared to a placebo, which is a shot of nothing, essentially. And let's say that resources are limited, which is always true. It costs a lot of money to make that trial vaccine. A lot has to go into it. Let's say your supervisor says to you, we can give you enough resources to test 30 people. Now, you don't know if 30 people's enough for you to really get enough data to be able to make inferences to the population as to whether the vaccine works at the population level, which is, of course, the real question of interest. So as a statistician, you might go back to your supervisor and say, look, supervisor, I love you and all, but I'm concerned about the issue of statistical power. I'm concerned about whether my research design is powerful enough so that if I should reject the null hypothesis, I likely will reject the null hypothesis. So the question of statistical power is not whether you're rejecting the null hypothesis or not. Rather, it is asking the question based on your methodological design, which we'll be talking about. It's asking the question of whether you are likely to reject the null hypothesis if indeed your research hypothesis is correct. So that's the basic question of statistical power. Again, from a methodological perspective, from a researcher's perspective, it is a wickedly important kind of question. And as you'll see, it embeds lots and lots of concepts from this course. So if you can get your mind wrapped around computing statistical power, you really have a strong and deep understanding of the concepts from this class more generally. So let's start with a question. You work for a company, and one of your goals in the Human Resources Office is you want to reduce absenteeism. You want your people to go to work, and you want them to be healthy, partly because you want them to be healthy, partly because you want them to go to work. So here's a situation. Imagine you're doing a study where you're trying to see if people who take daily vitamins miss fewer work days compared with the general population of workers. So you're asking this general question: do vitamin takers miss fewer days? As an employer, that could be an important question, because if you find evidence that vitamin takers do indeed miss fewer days, they're healthier, they're less likely to take sick days, etc., then that's great. You don't want your employees missing work. The whole point of work is work. So here's the question: do vitamin takers miss fewer days than the general population? I'm going to give you some information. And you're going to see with the power example, you are given more information that might even seem reasonable in some cases. Okay, so I'm going to give you mu sub 2. Mu sub 2 equals 4. That is the population level mean for the number of sick days that employees at this company take per year. 4 sick days per year. I'm going to give you sigma sub 2, which equals 1. So the population level standard deviation for the number of sick days taken by employees at this company is 1. I'm going to give you an alpha of 0.01, or 1%. If we were going to carry out the hypothesis test, we were going to be very conservative here. We're going to have an alpha of 0.01, meaning that we'll only reject the null hypothesis if we find evidence against the null hypothesis that happens less than 1% by chance alone. So that's considered a very conservative alpha level. 1%, alpha equals 0.01. I'm going to give you an n of 10. So your supervisor is saying you're allowed to study 10 people in this study. And I'm even going to give you, this is the part that seems a little sketchy on how I'll explain it. I'm going to give you M. Remember, M means sample mean. I'm going to give you M representing the special population, which in this case is vitamin takers. M equals 3. So we're going to make an assumption. The assumption is that the hypothesis is true, and the assumption is, more specifically, that the mean for the special population of people who take vitamins is 3. On average, we're saying that the number of sick days that the vitamin takers take is 3 compared to 4 for the general population. Now, I'm going to give you a little sidebar. A lot of times this is where really smart students will raise their hand and say, well, this is stupid, how do we know this information? And if we knew this information, we wouldn't need to carry out the hypothesis test. I'm not going to argue against that. I'm not going to disagree with it. In the real world, these numbers are kind of ballpark numbers. These are numbers that you, the researcher, sort of come up with. It could be based on past research. It could be just based on assumptions that you're making. It could be based on numbers that you think would actually matter. But you're kind of coming up with this as an assumption, simply to work out your estimate of statistical power, knowing full well that that number is, in fact, based on an assumption that is kind of grabbed out of thin air and that you don't really know. So you're essentially saying, what would my statistical power be, assuming that the mean for the special population is 3? That's really kind of how we're thinking about this. So we're going to compute statistical power given all these parameters, all this information up here. Steps in computing statistical power. Step number one you're going to like, because step number one is the same as it is for hypothesis testing. Step number one is we're going to articulate H sub 1 and H sub 0. So we're not going to carry out the hypothesis test, but if we were going to carry out the hypothesis test, we would need our hypothesis demarcated. Okay, so mu sub 1 corresponds to vitamin takers. Mu sub 2 is the general population. And the research hypothesis is that mu sub 1 is less than mu sub 2. In other words, the average number of sick days taken for population 1, the special population of vitamin takers, is predicted to be less than the number of sick days taken by the general population. The null hypothesis, as you recall, is the opposite of the research hypothesis, and it always includes an equal sign. So mu sub 1 is greater than or equal to mu sub 2. Step number one is exactly what we've done before. You're going to like this, kids. Step number two is exactly what we've done before. Step number two is the comparison distribution. The comparison distribution is a distribution of means. Okay, I'm drawing it down here. Comparison distribution is a distribution of means based on an N of 10. So it's as if the stats-friendly giant went into the population of employees, randomly took 10 of them, asked them how many sick days they took, put them back, and did that infinitely. So the mean, what I'm going to call mu sub m sub 2, is the mean of the distribution of means based on an N of 10 for the general population or corresponding to the general population, and it is 4. So the mean of our comparison distribution is 4. If we were going to carry out the hypothesis test, which we're not going to, but if we were going to, this would be the comparison distribution. The other parameter we need is sigma sub m sub 2. That is the standard deviation for the comparison distribution. So you remember, to get sigma sub m, we're going to get sigma square sub m, which equals sigma square over n, which equals 1 squared over 10, which is 0.10, and sigma sub m, or in this case sigma sub m sub 2, is the square root of sigma square sub m sub 2, is the square root of 0.1. My calculator is saying that is 0.32. Okay, so that's our comparison distribution. I'm going to give you a little sidebar right now, kids. I'm going to put it in this little box that I'm going to draw, and then I'm going to erase it, and I'm not going to talk about it too much more. But here's my sidebar. You see my sidebar right here? There's an assumption of what we call homogeneity of variance. There's an assumption of homogeneity of variance. Homo meaning same, gene meaning kind, so homogeneity meaning of the same kind. In a lot of our stats, including everything that we're talking about here in chapter 9, this will also be true in chapters 10 11 and 12 actually, there's an assumption that the kind of variance, meaning also the kind of standard deviation that we have for two different populations, is the same. So our hypothesis test is often about how means are predicted to be different, but we are not usually assuming that variances or standard deviations are predicted to be different from one another. So there's an assumption of homogeneity of variance. That kind of means in this case that if sigma sub m sub 2, the standard deviation corresponding to the distribution of means that corresponds to the general population is 0.32, that means we're essentially also saying sigma sub m sub 1 equals 0.32 as well. There's an assumption, the assumption of homogeneity of variance, that these standard deviations are identical to one another. It is the content of more advanced stats classes as to why we make that assumption, as to what we call what happens if there's a violation of that assumption, what are the statistical ways that we can use to figure out if that assumption is a good assumption or not a good assumption. But for this particular class, we're simply going with the assumption. When you get into your PhD program, you can poke around on the details and the mathematical parameters of that assumption. But for now, we're going with the assumption of homogeneity of variance. That's a little sidebar, kids. It's gone. Okay, question, step number 3. This is still the same step as it would be if we were going to carry out the hypothesis test. Step number 3, we're going to figure out Z critical. If we were going to carry out the hypothesis test, we're not going to, but if we were going to carry out the hypothesis test, we would need to figure out Z critical. Z critical is going to offset our alpha region. You remember that alpha and Z critical follow the research hypothesis. The research hypothesis is that mu1 is less than mu2. Therefore, our alpha region is over here. This is 1% of our distribution. That's alpha. If we were going to carry out the hypothesis test, this is where our alpha region would be. And this z-score, what we're going to now call z-critical, is going to be the z-score on this distribution, which corresponds to having 1% of the distribution there and 49% of the distribution here, between that particular z-score and the mean. So we're going to go to our handy-dandy table, and we're going to look up 49%, because you remember the table gives us the percent between the mean and a particular z. So we're going to look up 49%, and here we go. And we got 49.01%, not exactly 49%, but that's the closest, and it corresponds to a z of 2.33. And the only thing I'm going to do is add negative. So z critical equals negative 2.33. It's negative because it is to the left of the mean. Whenever you have a score that is to the left of the mean of a distribution, it has a negative z-score. So z critical equals negative 2.33. So there's your step 3. Step 4. We're now going to do what I call shade the alpha region. I'm going to use my pink for that, kids. I'm going to shade the alpha region. If we were going to carry out the hypothesis test, which we're not, but if we were going to carry it out, we would need to get a z obtained that would be on this lower distribution, on this distribution here, so extreme that it was in this alpha region, this pink region. Now, before I go on, I'll give you a conceptual way to think about power at this juncture. Power is going to correspond to another distribution. There's a distribution, I'm going to draw it soon, which corresponds to the vitamin takers. And the question of power kind of is the question of what percentage of that upper distribution, corresponding in this case to the special population of vitamin takers, is extreme enough to reject the null hypothesis on this lower distribution. So step number 5 is to actually draw that upper distribution. So we're going to draw the upper distribution, and I'm going to let that line not touch the upper distribution. I'll show you why in a little bit. But the upper distribution, let's see, it looks like I'm going to have to erase a lot of stuff up here. The upper distribution corresponds to my special population. Okay, so the mean of my upper distribution is mu sub m sub 1. It's a distribution of means, so it's represented by mu sub m. I put that as 3 before. The standard deviation is sigma sub m sub 1, which is 0.32. Remember, that's because the assumption of homogeneity of variance. So sigma sub m sub 1 equals sigma sub m sub 2. The mu sub m sub 1, we're going to use the mean that we got as given information at the beginning as a proxy, as our best proxy for mu sub m sub 1, for the mean of that distribution of means corresponding to the special population. So there's the upper distribution. Importantly, the mean is appropriately placed relative to the mean of the lower distribution. Okay, so the mean of the lower distribution is 4, the mean of the upper distribution is 3. That's why that entire upper distribution is shifted, as you can see, to the left of that lower distribution. Okay, so it's intentional. All that matters in terms of getting this correct is that this mean is, in this case, to the left of the mean down here, because you're predicting that mu sub 1 is lower than mu sub 2. If mu sub 1 were predicted to be higher than mu sub 2, that mean for that upper distribution would be shifted over to the right. So now we're going to do what I call compute and demarcate M critical. Okay. These things are on different scales. This one has a mean of 3, this one has a mean of 4. How do we deal with numbers that are on different scales? We deal with them in terms of z-scores. So here we have a z-score of negative 2.33. Whatever this score is down here corresponds on this lower distribution to a z-score of negative 2.33. However, that same raw score is going to actually correspond to a different z-score on that upper distribution. Because what a z-score is, it is the number of standard deviations above or below the mean a particular raw score is. So now we're going to get what I'm calling M critical. It is the z critical converted to a raw score. And the raw score in this case is not x, but it's m, because m is a sample mean, and the raw scores in this distribution are sample means because it is a distribution of means. So that's what the raw scores are in these particular distributions. M critical equals, it's just converting this z critical to a raw score. So it's z critical times the appropriate standard deviation, in this case sigma sub m sub 2, plus the appropriate mean, which in this case is going to be mu sub m sub 2, which equals negative 2.33 times 0.32 plus 4. Time to hit the calculator, kids. I'm getting 3.53. Dana, did you get that?
Hold on. I might have done it wrong. Can't. Is it 2.33?
Yeah, negative 2.33.
Yeah.
Okay, 3.53. Okay, so this critical score, this Z critical down here, corresponds to what I'm calling M critical of 3.53.
Oh, I actually have 3.25.
Whoa!
5.
So I wasn't even close. Let me do that again. Sorry,
Yes,
kids.
harder on
0.32
the
times 2.33. Okay, so it's negative 0.75 plus 4. Oh yeah, so it's just 3.25.
Yeah.
Okay. Thank you, Dana. Okay, let's think about what that means. The M critical is 3.25. That means if I were going to carry out the hypothesis test, which I'm not, but if I were going to, the mean representing my special population would have to be 3.25 or less, which would correspond to a z-score on this lower distribution of negative 2.33 or less. So all the 3.25 is, it's just a raw version of what that z-critical is. And that's important because this upper distribution right now is in the world of raw scores. So now that we have that M critical of 3.25, we can start to think about, well, where is that same score on that upper distribution? So point number 7 is what I call M upper. Again, once we have that z-score converted to a raw score, in this case 3.25, we now can place it on that upper distribution appropriate to the mean of that upper distribution. That upper distribution is 3.25 over here. So M upper simply equals M crit. And you're going to see, I'm going to put it up here, M upper equals 3.25. Okay, I have drawn it on that upper distribution relative to the mean of the upper distribution. 3 is over here, 3.25 is over there to the right of it, as opposed to down here, which has a mean of 4, and 3.25 is to the left of it. That's important. Okay, I haven't yet joined these worlds of those two distributions, but we're close. Okay, the next thing we're going to do is compute what I call Z upper. Okay, think about what a z-score is. A z-score is telling you where a raw score is in a particular distribution relative to the mean and standard deviation of that particular distribution. Okay, so Z upper essentially means we're converting that raw score, 3.25, I'm calling M upper, into a Z score. not a z-score on that lower distribution. We know that that corresponds to a z of negative 2.33 on that lower distribution. But what is 3.25 as a raw score converted to a z-score on that upper distribution? So z upper equals m upper minus the mean of the upper distribution, mu sub m sub 1, divided by the standard deviation of the upper distribution, sigma sub m sub 1, which equals 3.25 minus 3 over 0.32. It's calculator time, kids. And my calculator is saying 0.78. Okay. 0.78. So this score is an upper distribution of 3.25 as a raw score on that upper distribution. Corresponds to a z on that upper distribution of 0.78. Meaning that on that upper distribution, that raw score of 3.25 is 0.78 standard deviations above the mean on that upper distribution. So the same raw score, 3.25, has a different z-score depending on the distribution that you are dealing with, and that is critical in understanding power. So that's z upper. Step number 9, we're going to connect z upper and z critical. Okay, here's the most important thing that I cannot underscore enough, is that when you do this step, step number 9, connect those points with a non-straight line. And I'm only going to tell you that because if you force yourself to use a straight line, you're going to mess it up. What matters isn't that it's a straight line. What matters is that they connect where they are in terms of raw scores. So here's 3.25 down here. Here is 3.25 up here. You'll see that I curve that line. That is okay. That's okay that I curved it. What matters is that both of these points, this point here and this point here, I'm going to give them a little purple. Both of those points are 3.25. Both of those correspond to a raw score of 3.25. So there I am connecting them. Now, we're just about done with the problem actually. Step number 10, we're going to shade power on the upper distribution. Okay. Dana, what color do you want to go with?
Green.
We're going with green, kids. Our associate producer Dana is saying we're going with green. Okay, we're going to shade power on that upper distribution. Let's think about what power means. Power corresponds to the ability to reject the null hypothesis. Everything that is to the left of this point would reject the null hypothesis if we were going to carry out the hypothesis test. Everything to the left of this point, everything to the left of 3.25 would be extreme enough to reject the null hypothesis. Well, everything to the left of 3.25 in that lower distribution is alpha, because that's our alpha region. However, let's go up here. Everything to the left, ooh, the green came out very nice, Dana. Good call. Everything to the left of that same point as a raw score of 3.25, everything to the left of that on that upper distribution is power. If we were going to carry out the hypothesis test, any score from to the left of that point would be extreme enough to reject the null hypothesis. So that green area is power, which is the probability of rejecting the null hypothesis if we were going to carry out the hypothesis test. So that's step number 10. We're just about done. Let's go to step number 11. Compute power based on the shaded section. So now we're going to compute power. Okay, computing power is essentially figuring out what percentage of our upper distribution is this green shaded area. Well, remember, whenever we have a thing like that, we can put that into A, B, and C. Section A is part of power, right? That's shaded, that's 50%. And section B is also shaded. So we need to figure out what section is section B. Well, section B is cut off by this z-score of 0.78. So if I look up 0.78, as a z-score, I will see that corresponds to a percent mean to z of 28.23, right there. So section B is 28.23%. In combination, section A and section B is power. That's our shaded area. Power is 50 plus 28.23, which equals 78.23%. That's power. We're not going to carry out the hypothesis test. But if we were going to carry out the hypothesis test, 78.23% of the time we would reject the null hypothesis. So that's how powerful our design is. I'm going to give you step number 12. Which is computing beta. Different from the beta from multiple regression, by the way. Beta, graphically, beta can be thought of as section C in this particular case. Beta is the entire part of the upper distribution which would fail to reject the null hypothesis on that lower distribution. Beta literally equals 100% minus power, which in this particular case is 100 minus 78.23, which is 21.77. Okay, so 21.77% is section C up here, by the way. That's what beta is. It's just the complement to power. And it's 21.77%. So I'm not going to carry out the hypothesis test, but if I were going to carry out the hypothesis test, the percentage of the time that I would fail to reject the null hypothesis would be 21.77%. Those are the steps in computing power. Before we finish this unit on power, I want to talk about 4 factors that affect power. Because when you're designing research, you really want to increase your power. By definition, power is a good thing. It's the ability to reject the null hypothesis when you should be rejecting the null hypothesis. So let's talk a little bit about 4 factors that affect power. One thing that affects power is the number of tails. One or two. Remember from the prior chapters, a couple chapters ago, chapter 6, I think, chapter 7 maybe, we talked about the fact that a hypothesis test could be directional or non-directional. If it is directional, that means that you have what's called one tail. A one-tail test, and you're only interested in rejecting null hypothesis based on one particular tail of the comparison distribution. If you have a two-tail test, then you divide alpha among two different tails, or between two different tails, and that makes it harder to reject the null hypothesis. Anything that makes it harder to reject the null hypothesis means you are reducing your power. So two-tail tests are less powerful than our one-tail tests. Number 2, effect size. Effect size is an index. We've talked about this earlier in the semester, now it's coming back. It is an index of how big your effect is. Effect size, depending on your statistic, can be measured in a bunch of different ways. For chapter 9, effect size is represented by something called Cohen's d. Married couple, Cohen and Cohen, wrote a stats book years ago where they developed this famous effect size. They named it after themselves, Cohen's d. And it equals absolute value of mu1 minus mu2 divided by sigma sub 2. Here's an important thing about all measures of effect size. Measures of effect size are always separate from sample size. Effect size doesn't care about how big your sample is, whether it's big or small. And because of that, we use population level parameters in coming up with our measure of effect size. So here, instead of mu sub m sub 1, we have mu sub 1. They're mathematically equal, but they mean something different. This is the population level mean for population 1, minus mu sub 2, or population mean for population 2, the general population. And here we have sigma sub 2, not sigma sub m sub 2. So now we're dividing by our best estimate of the population level standard deviation, not the standard deviation of the distribution of means. Effect size is always independent of sample. Distributions of means are always highly tied to the size of the sample. In this case, effect size is going to be the absolute value of 3 minus 4 divided by, what was my sigma that we started with on that?
1.
1. 3 minus 4 divided by 1, absolute value equals 1. So our effect size is 1. You're probably asking yourself, what does that mean? It's not a bad question. I will tell you that the Cohens, being smart, practical people, came up with an answer to that. So a small effect size is approximately 0.2. A medium effect size is approximately 0.5. And a large effect size is approximately 0.8. So these are called standard effect size conventions. You can see our effect size of 1 is very large, right? If 0.8 is large, then 1.0 is very large. The bigger your effect size, the more power your study has. Number 3 has to do with population variability. Population variability, sigma squared. the more that your population, or the more that the scores in your population vary from one another, the less power you have. The more that your scores in your population are similar to each other and vary less, the more power you have. So as population variability increases, your power decreases. Finally, I'm going to talk about sample size. As n increases, power increases. And this has to do with the comparison distribution and how your standard deviation of your comparison distribution will go down as your n increases. So it's easier to reject your null hypothesis as your n increases. A lot of times when people are talking to you about research, they'll say you want as large of an n as is humanly possible, and this is the specific reason that people will tell you that. So there's your factors that affect power. There's your chapter on power. This has been Glenn. Stats with Glenn.